So next up, we'll be hearing from William Yingling about impact melt emplacement on terrestrial bodies.
I'm Will Yingling. I work with Dr. Catherine Niche and Dr. Livio Tornabene at the University of Western Ontario. Today I'll be talking about impact melt emplacement on terrestrial bodies, particularly focusing on Mars and how it relates particularly to the moon. Impact melt is commonly found in and around craters. During an impact event, there is vaporized rock, there's melted rock, and largely displaced rock. And so we're focused on the melted rock. And we particularly want to know how the rock, the melt, goes from inside the crater to outside the crater. And so we see a very famous example here of Tycho crater on the moon with melt to the southeast here. And we can see some clear examples of melt happening on the moon. So there's also impact melt on different worlds, particularly the study focused on looking at complex craters. And so there's complex craters, we see them on Mercury, Venus, the moon, Mars, even Ceres, and the Earth. So that's what we're focusing on for this thesis. To introduce the problem is that so as I mentioned earlier, is that we're looking to see how melt goes from inside the crater to outside the crater. And so we have two emplacement hypotheses that have been established for the moon and for Venus. For Venus, it generally has melts, and the energy imparted from an impactor is imparted into the melt, and which is able to push it up and over the rim during the excavation stage of emplacement. And just as a general reminder, we have our generally three stages of cratering process for the contact and compression stage, excavation stage, and the modification stage. So for Venus, it happens during the middle of the cratering event. For the moon, however, there are generally deeper craters than we see on Venus due to the inverse gravity scaling law. And there's generally smaller volumes of melt. I believe the difference in impact, the mean impact velocity between Venus and the moon is the Venus has about 25 kilometers per second, whereas the moon has about 19 or 20 kilometers per second average impact. What likely happens is that the energy, there's not enough energy from the impactor to push the melts up and over the rim, but rather the rebound mechanism that takes place during the modification stage likely adds to the momentum and is able to push the melts at the lowest potential energy barrier of what we call the rim crest low. So just basically the lowest point along the crater rim is where melt is preferentially going to cross over the rim. So we have we have melts on Venus. In this example, we have Xantippe crater, where we have melt to the southwest, this very striking swath of melt in this radar image. Very clearly, the direction of the melt is to the southwest. And we also have a DTM here for panel B, which can you see that okay? Okay. So for panel B, there's a DTM, and the rim crest low, so to speak, is to the north. Is you can see that there's a depression to the north, and so we consider that the rim crest low. And so what we then do is then we put those two together, cardinal directions, and then we is 135 degrees. And for the moon, we have another example of a crater with melt, Ohm crater here, where the melt, we have this nice zoom in picture of melt happening just to the southeast of the crater, where you have distinct surface roughness changes. You have distinct albedo contrast for the melt happening itself, but that's not necessarily as easy to see on Mars. So we have a different classification for that, which I'll get to in a second. And then for panel B, we have a rim crest low also to the southeast, likely because the pre-existing topography was already depressed. And so in this case, the melt distribution direction and the rim crest low, we say coincide, so lie at 0 degrees. So for Mars, how do we categorize melt? Is that since Mars has an atmosphere and it's dusty, we need another characteristic to help identify melt. So what we can use is crater-related pitted materials, which are quasi-circular depressions that occur in dense clusters with also subtle raised rims. And so the melt that these are found in often occur at topographic lows as well. So these crater-related pitted materials are important because they're associated with the volatile rich nature of the Martian regolith. And so we don't necessarily see these on the moon. It's not observed on the moon, or Mercury for that matter, since they're volatile pore bodies. But we do see them for Ceres and Vesta, which are also volatile rich. So for mapping examples, is that we have a couple of examples here of craters that I've mapped on Mars. The colors aren't necessarily too important in this case, just that the melt distribution is the important part. So we can see the clusters of melt distribution, and we can decide where the melt distribution is that way. And then from there, we can take the next step and make DTMs, and then assess where the rim crest low likely lies. And so we can do this either visually, or we can use basically ArcGIS, ArcMap to do a tracing of the crater rim, and that'll tell us exactly what the elevation profile of the rim is at every point. So for these cases, we have the rim crest low at these directions. Okay. So back to our mapping examples. We know the melt distribution, and we know the rim crest low direction. And so then we can categorize coincide, or for example, they're 90 degrees or greater. So how does this relate to other bodies in the solar system? So Mars looks, so our sample size is relatively small with just 12 craters compared to the 49 or almost 50 craters for the moon. But Mars can tentatively be grouped with Venus and Mercury. So what does that ultimately mean? Is impact, melt, and placement on the moon seems unique amongst the terrestrial bodies, at least so far. We could see more follow-up work with on Mars or on Ceres even, but it would seem that surface gravity appears to play the bigger role in melt and placement than impact velocity in this case. And yeah, that's my talk.
Okay, great. Thank you, Will. I think we have a minute or two for a couple questions, if anybody has any. And if not, I'll start off with one. So you're talking about the terrestrial bodies, and I noticed you did not include Earth in that category? Is that a reason for that, or are the impact craters on Earth not super useful for what you're doing?
We haven't seen a whole lot of impact melt is very hard to, it gets eroded very quickly. And so we don't see it nearly as much on Earth. So that's why we're looking to Mars.
Right. Awesome. Thank you.
Okay.